Okay, welcome everybody. This is a free webinar provided by ISPC, a 501c3 not-for-profit organization on cable splicing and terminations, hosted by Tony Boyd, ISPC senior consultant. Um, we will have a donation button in the chat should you choose to donate to ISPC's mission to promote safety in the power and maintenance industries. This is how we can put on some of these free webinars. So the donation is a tax deductible donation, and we can send you a letter verifying your donation for tax purposes. So thank you all for your support, and without further ado, I will hand it over to Tony Boyd.
Thank you, Ryan, and welcome everybody for the free cable splicing and termination webinar. This is actually some on-site training that we do. It's a all day, depending on how many folks we might have, but we go through this class. It's usually about 3 hours. We give a little test at the end just to see how the instructors are doing. But we usually give this on site and actually bring some cables and have some cables and make some splices and some terminations and things like that. So you'll see, well, go through this pretty quick because 4 hours that we have about an hour. But if you have any questions or comments, you can certainly raise your hand. That's why we have Ryan online, so that he can see anything like that. Interrupt me because I'm going to be going through my slides, and I might not see if you have any questions or comments or anything. They're certainly welcome, and we appreciate any kind of donation because we are a not-for-profit. So why are we doing a free webinar? Well, we're just trying to let folks know what we have. There's a lot of people out there that and companies that don't know what we do. So we're just trying to promote what we do and promote safety. And that's basically what this is about. We have a sister company called T&D Power Skills. So that's where a lot of this information comes from. Mac Turner, Jim Vaughn, and I are subject matter experts for the T&D Power Skills line worker training program. And so, that's where a lot of this information comes from. And we're certainly thankful and grateful for all you folks that support us in these endeavors. I'll talk a little bit about PPE. We'll breeze through work area safety, and then we'll spend a little bit of time talking about the types of electric URD cable and then the splices and terminations. So PPE, depending on what your company requires you to wear. If you look, this guy will start at the bottom with his rubber overshoes, and are rubber overshoes required when you're standing on a grounded mat? And the answer is certainly not everyone requires that. The rubber overshoes are basically to enter and exit that grounding mat. So they're a good idea. I'm not going to give my personal opinions about what the rubber overshoes do, but they do provide some protection. How about that? Rubber gloves. You see he's using a hot stick with rubber gloves. I have never been a proponent. ISPC has never been a proponent of wearing rubber gloves when using a hot stick. And you notice it's a shorter hot stick. Most of the shotgun sticks nowadays are 8 foot long, which gets you back away from what the hazard actually is. So we do not require rubber gloves with hot sticks. And basically that is because when you're handling a hot stick, you need to be in positive control of the energized conductor, whether it's an elbow or overhead jumper or whatever. You have to be in positive control, and sometimes wearing rubber gloves does not allow that. I was a little bit thin back in my line worker days. So when it came to some of those big elbows, I actually had to take the stick and put it up under my arm to pull it. So what are rubber gloves doing? And I'm not going to get into the electrical properties, but that's some of the things that we cover when we're on site. Then you see the FR clothing, hard hat, safety glasses. Some companies actually require a face shield when switching underground primaries. So basically, I bring this slide up and ask the folks uh, about documentation of your PPE. So the guys got some rubber gloves. We usually document handing out rubber gloves because they're so expensive. We want to know what their test dates are and things like that. But do we do the same with hard hat and safety glasses? And there's a lot of companies that I've been to in the last several years that have never actually documented issuing safety gear, safety glasses, hard hats, whether it's work gloves. Um, but it's something that we really need to do. OSHA says 1910-134, the employer shall provide training to each employee who's required by this section to use PPE. Many times we just take for granted that this person knows how to put a hard hat together. But do they actually know how long the hard hat should last? Do they know how to inspect the hard hat, see if the headgear is actually coming apart? I've made it a Christmas present, birthday present. My birthday is in November, so every November I buy myself a new headliner because I sweat so much during the summer. I don't want to wear the thing more than just during that summer. So, just a few little things like that. So OSHA requires us to document training when PPE is necessary, what PPE is necessary. Do we have to wear our safety glasses all the time? What about our hard hats? Do we have to wear a hard hat in a vault? A lot of companies have different safety rules governing what their employees should be doing. How to properly put it on, take it off, how to wear it, and what are its limitations. I see a lot of companies, especially contractors out there. The guy looks like he's got some really good Z87.1 safety glasses, but they might be an off-brand, just really cool looking glasses, but they don't have the impact resistance of the Z87.1 standard. So we do need to make sure all of our folks know what PPE is required, when they should wear it, where they should wear it. Getting into the work area safety. What are safe working conditions? What about safety, traffic safety? The tailboard and the pre-job briefing. What are some physical safety barriers? And how do we identify circuits? We'll cover all of this very fast. But in this picture, you can see we have some underground facilities. What are the hazards? Whether we're digging, whether we're opening up a pad mount transformer. What about the customers that live in the house? When a company truck pulls up in front of their house, they're wondering, are you going to turn my electricity off? So, we may have to deal with some customers that they may have had their electricity turned off before. So now they're not so welcoming for your guys that might be pulling up. What are some of the hazards in the work area? You see here some worker signs. Do we need a flagger? And yes, if we do need a flagger, we should at least have some training for that flagger, and we should also put a flagger sign out to warn motorists that they're coming up to an area that is being delineated by a flagger. The tailboard conference. Is everyone involved in the tailboard conference? Pre-job briefing, JHA, JSA. Every company calls them just a little bit something different. What OSHA says is, what are the existing characteristics and conditions of the area that we will be working, and what needs to be covered. At least hazards associated with the job, tripping hazards, falling hazards, dropping equipment hazards. I'm not going to spend a lot of time there. Work procedures involved. Does everyone know what we're going to do? Any special precautions? Is there anything in the area that we need to be aware of? I always add in there, what is our emergency procedures? What if someone gets injured and things like that? What do we do? What is our procedures? Make sure everyone knows especially what we're doing and where we are. The energy source controls, we have electricity. Where does it come from? What's feeding it? Is it a recloser cutout? Things like that. And then what PPE are we required to wear on this job site? Do we have to have vests for this part? What about earplugs? Are we using some machinery that we may need some extra earplugs or something for that? Some of the physical safety, manhole entry. I have found that a lot of folks out there do not realize that you shall test the underground facility. That's why your manhole covers have a hole in them. So before the cover is ever removed, you should test to see what the atmosphere or any gases are like inside the manhole. Lifting the cover. Do we do back-breaking jobs while lifting the cover? There's so many tools and pieces of equipment now that we can actually use to lift the cover, so we don't have to hurt our backs anymore, like the picture on the bottom right-hand side. Tools lowering. If anyone is throwing their tools down into the vault or throwing them back up, we should get a hand line and actually pass the tools back and forth. And some physical safety, inspecting the area. I remember it's been a long time ago, but I had to work in a rear lot, pad mounted transformer. We opened up the transformer. Everyone was getting tools together. There was 3 of us on site. We were getting our tools together to do the work, and we did not see the golden retriever that was curious, came up and tried to sniff the 120 volt top secondary bushing, got his nose connected to it, and shocked him pretty good. Didn't kill him, but we got lucky on that one. Inspecting the cabinet is always part of any kind of physical safety before we ever open the cabinet. So OSHA says working on exposed energized parts. You see the little red highlighted section there, proper use of special precautionary techniques. So we should be familiar with what our techniques are in inspecting our equipment and things like that. Inspecting the cabinet, the hinges, the door lids, things like that. And the selection of use of work practices. How do we do that? I've discovered in the last few years there are slings for actually setting and replacing pad mounted transformers that hold the door open. Back in my days as a young man, we had to rely on somebody that could hold that door open while we were setting and removing the transformer. So just some of those special things that needs to be taken into account. Phase identification, where different phases are in the same vault or transformer or in the same vicinity, they shall be identified. I actually had several crews that worked for me years ago that's all they did was go around to subdivisions old subdivisions that were installed back in the 70s and 80s that were not identified, and that was their task, was to identify cables, and it was a very difficult task to do. Where different phases are in the same vault enclosure are parked in some manner that could be looped, these phases shall be marked or identified. Did we just have a question? Did somebody just have a question, comment?
No, Tony, no. Somebody was just saying they came in late and was apologizing for their lateness.
Oh, okay. Well, glad to have you, even though you're late. You just missed the introduction. Now we're going to get into the cable itself, is why everyone is here, cable splicing. So we'll talk about the different kind of layers of cable, the insulation, the concentrics, the semiconductive layers. So there's paper insulated lead sheath cable, and you may be surprised that there is still hundreds of thousands of miles of paper insulated lead sheath cable that are still in use since the 40s and 50s. It was an excellent, well-made product, and a lot of the folks that are splicing and keeping this energized are retiring and don't seem to be passing on the knowledge that they have to the younger folks, because we get calls on a regular basis to come do some training on paper insulated lead sheath cable. Another one is the EPR rubber, the insulation, then the cross-linked polyethylene, very popular. And then we have copper concentric wires and copper tape concentrics. So just the different types of cables that are out there, different rated primaries and secondaries for the different types of cables. This is the EPR rubber. So you see I'll start from the left and go to the right. So a G is your jacket, and it has all the information on there. And most of the time, all the companies now actually give you a foot mark on there, so you don't have to try to guess how much, we need 80 feet of cable to go in here, or 180 feet of cable. We can actually do some math and look on the cable reel and see what the footage is. F is our semiconductor concentric, and then the semiconductor shield is E, the insulation is D, and then we have a conductor, a semiconductor on the conductor itself. Actually, I'll go into this in a little bit, but basically it just takes the conductor and makes it perfectly round for stress control. All right, cross-linked polyethylene, you see it's more white. It's a little bit stiffer cable than the rubber. The rubber will actually flex a little bit more, but it's, to each his own. Some companies like the rubber, some companies like the cross-linked polyethylene. Talk a little bit more about that when we get into the stresses, but you see on this one, just like the last cable, the conductor, and then the conductor shield, and then the insulation, the semiconductor insulated shield, and it is a semiconductor, even though it's made of a rubber compound. It will still conduct, and we'll talk about the purposes of that in just a little bit. We have the metallic shield, neutral conductor, and then the jacket, just like the other cable on here. All right, in the bottom left, you'll see 3 conductors in one cable. Very common in some areas of the country, especially islands. They like to run a lot of this called submarine cable. All 3 conductors are in the same jacket, and all 3 use the same concentric, as well as having their own concentric, and we'll talk a little bit more about that. We kind of get into the concentrics and what the hazards are back toward the end of this. So you see we have jacketed, some cables of old were unjacketed cables, so the concentric was actually exposed to the elements and caused some problems in some areas. If that concentric is not conductive all the way through, it may create some problems with the cable itself, and I'll talk a little bit about that coming up right here. All right, this is what we're all waiting for: the voltage stress when the cable is terminated. The semiconductor insulation shield, which is in contact with electric ground, must be kept at a safe distance from the conductor and connected equipment. That distance must be sufficient to avoid a direct path to ground. So to maintain a safe distance, the semiconductor insulation shield is cut and a portion of it near the end of the conductor is removed. When that's done, however, there's no voltage stress beyond what we're talking about. So basically, you can see right in here a low point and a high point. So the semiconductor that goes around the conductor is actually lessening. All right, don't click this time. It's actually lessening these low points and high points, so that the stress is actually going through the insulation evenly. Now, someone may ask, is there any leakage? And the answer is yes, there is. So there's that conductor shield layer, which tells us that it's evenly bringing those stress lines out of the insulation. There is some current leakage across insulation, any insulation. When it is energized, we'll have some current leakage, and cables, uh, your booms on your bucket trucks, your hot sticks, your shotgun sticks are all designed for this current leakage. It's very, very small. If we got a measurement on it, a lot of times it's so small that it would take a micro amateur to actually get a reading on it. But yes, it does allow some leakage, and the whole purpose of that conductor shield layer is to make that leakage evenly. And so the stress lines are now concentrated toward the bottom of the conductor in this picture. All right. And when we add that insulation shield on top of the insulation, that's what causes the stress to go out evenly all the way around through the insulation. It's such a minor leakage current. Excuse me for the sniffling. These pine and oak pollen is getting to everybody around. All right, so the insulation shield actually makes the stress lines go out evenly. So, to deal with the problem of stress concentration in the area of insulation near the bottom of the conductor, the semiconductor insulation shield layer is added over the primary insulation to provide a uniform ground around the primary insulation. So that is why it is so important not to nick this insulation shield when you're skinning back the cables. And I'll talk a little bit more about that in a minute. And here we have one that is actually cut back thanks to some of our 3D illustrations. You can see the red insulation and the conductor, the semiconductor, the insulation, and then the semiconductor shield underneath those concentric wires. So basically, the stress when we cut off that insulation shield and we're terminating to make a splice or a terminator, it creates an extra stress going back over that semiconductor trying to go to ground, and the leakage current is exceeded. So we need to build up a stress cone. Let me see if I can get my arrow back over there to it. And that's basically what this is showing, is a stress cone. So it allows us some extra insulation for that stress that is coming up and trying to go back over it and get to ground. So here, all the stress lines are even. Here, they're going to concentrate because there is no more semiconductor shield. So that's why this part of an elbow or a terminator or a splice kit is so important. This area right here, because it's limiting the amount of stress that's going to build up and go back to ground. And I actually have something coming up that's going to explain that. So that distance is called creepage distance. All right, throw a little OSHA in here, training, and I thought I had some of it highlighted. Anyway, the training shall establish employee proficiency and work practices required. So if we're going to make up splices, we have to conduct our training in a manner that shows proficiency. So we come on site, we go through all this training, and then we actually have the guys make up some cables, make up some splices, use the tools properly. I don't allow a knife on any of the jobs that we're using. We have specialized tools that can do that. If your company does allow using a knife, I would suggest getting some cut resistance gloves for that, because it is the hazard. So anyway, all through here, demonstrated proficiency, and that's what OSHA is talking about in this training. We shall demonstrate proficiency and show that we know what we're doing in any kind of training. Splice kits. This is just one example of a 3M type splice kit, and let me just give a little caveat right here. We don't promote any one product or anything over any other product or any other type of tool. We are a not-for-profit, so we don't buy any of this. This is the customers that we've been out working with. This is just the type of tools and materials that they use. So on the left-hand side, we have a cold shrink, which is a pull tape that will allow it to shrink down. This company uses that to seal the semiconductor shield and the concentric wires so that no moisture gets in and affects the cable. On the bottom is the splice kit. This is for the range is around 175 mil type of insulation cable. And then at the top we have a 1/0. It's yellow, so it tells us that this is a 1/0 splice for the conductor. And you notice it's got a little bubble in the inside. This is very important for the stress in that splice body. If it gets offset too far one way or the other, and right here. So if this part gets offset inside that splice body one way or the other too far, it will actually create a stress point in this area and cause a fault across the grounded outer jacket. This comes in the kit. This is also a type of water sealant. So you can see at the end of the cable where we have our concentrics, and we have the jacket. We took the concentrics back so we can add that extra water seal on there. This company also requires this to go over that splice body. So I put this up here because instructions. I don't care how many splices your guys do or how many terminators they do. Most splice kits and terminator kits come with a template now. I always suggest that we use the template. We need to know what the measurements are in case the wind blows our template away. We need to know what those measurements are and how to use them. So here's some of the tools that this company used. And like I said, we don't promote any one brand over the other. There are other brands that will do the same thing, but starting at the top right, here we have a semicon scoring tool to score the semicon. Here we have an insulation removal tool. This will actually go in and protect the conductor, but take the insulation off. Here is just some needle nose pliers that we use for removing that semiconductor, and that's what this company uses. Back in my day, I used to actually use the, oh, come on, Tony. I used to use catfish pliers. They worked very well in getting that done. Here's just some regular pliers for twisting the concentrics. Of course, we have a ruler. Down here is a chamfer tool. Wow. And then you see the template that's used, some cleaner tape. This company used a white marker to mark, where they all go, and then a wire brush for cleaning the conductor, and then this is a crimping tool. Okay, so in our class we go over whatever tools you might have, and like I said, we're not promoting any one product over another. This is just what this company was using at the time. If your company uses something else, I would be more than happy to come and get pictures of it and show it into our slide presentations. All right, here's the one that we jumped to. This is just a couple of different types of crimping tools. One on the left is a hydraulic crimping tool. The one on the right is a battery-powered crimping tool. Some of the important distinctions when making crimps is depending on the type of die that you're using, you may have to rotate the press to keep the lug itself from what we call banana, getting a bend in it. So you always want it to maintain straight, and it's because of those stress lines that I talked about earlier. Faulty installation. All right, this is actually a cable that I got from on a job site from many years ago. It was a part of a terminator, And I made up one elbow, and the fellow sitting next to me made up the other elbow. And you can guess what he used to get the semicon off. Ding, 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 it was a knife. So when he was getting the semiconductor shield off, which is right here, his knife actually cut into the insulation just a little bit. So when we energized it, 1 year later, to the very month, is where this blew off. So basically, it was brand new. We energized it. There was hardly any load. 1 year later, we've actually put a little bit of load on this cable. So as we increase the amperage, we get leakage current, coming through to that one little nick right there, and it blew out. And so it actually tracked down to the concentric wires that were back here. So I like to show this picture just to show that the simplest little nick can create a problem. So the number one cause of cable failure is faulty installation. And that's always a test question. All right, special tools for scoring the semiconductor. And again, we don't promote any one tool over the other. There's several out there that can do the job. I just got the close-up of this picture to show that we need the tools for the scoring tool needs to be set proper so the installation underneath is not damaged. Another thing that we teach is a lot of your underground cables, well, all of your underground cables, come on a reel. So when they come on a reel, they end up with a little bit of curvature to them. So we train all of our cables to be straight when we're either making a splice or a termination. So we try to make sure that they're straight, because if we come through with a scoring tool on an angled cable, it may have a tendency to cut one side a little bit deeper than the other and damage the insulation. I usually get asked a question, hey, Tony, what happens if I damage the insulation? Well, we cut it off and we start over and hope that you have enough slack in that underground cable to actually pull up some more and make it up over again. A lot of folks using knives have gotten really good with their knives, and it's been an accepted practice. However, in the last 10 years, I have never allowed a knife to be used on a job site. I did have one company that provided us some cut-proof gloves, cut-resistance gloves, and so I let them use a knife, although I did show them how to use all of the tools so that you did not have to use any kind of a knife. Now, the jacket, there's a lot of companies that still allow their employees to use a knife to remove the jacket, and that's totally up to you. I will say, though, that there is a risk in letting them do that. All right, training the cables in a vault. It's always important, especially in a vault, large vault or small vault. It's important to train the cables, because when they come in from one way or the other, and as you can see, we had 3 phases that came in from the left side, 3 phases that came in from the right side. The important thing about training these cables in a vault is you may have one cable that has come in twisted this way, one cable that has come in and twisted this way. Now we splice them together and we go to lay them in a vault, and we untwist the conductor on the inside. I ran several contractor crews back in the day, and I won't mention the years. I've been doing this about 45 years now, so it was way back. And anyway, we had several installations where we've installed the cables, made splices, and 2, 3, 4 years later, as load comes in on these cables, because that conductor was twisted as it was laid down into the trench, it made a weak spot inside the splice, and we started having some splice failures. So training the cable is very important. So if it comes in one way, goes in the other way, we just want to make sure that when we're going to lay the cable down in there, it's not going to untwist that cable. All right, sliding the splice body onto the cable. This is usually the toughest part. You see the guy is actually holding the cable itself. They put, before this picture was taken, they put silicone on the cable. At the bottom right of this picture, you see the other end of the cable that's going to come on and be spliced. And like I said, this company uses those cold shrinks, so they went in and put the cold shrinks on before this operation. Now, the splice body, this company requires using gloves, and it's always a good practice to use gloves when doing this. But I always let my guys do it barehanded. They would clean their hands. That way they would not get any dirt on the splice body. A lot of times our gloves get dirty and get contaminants on I can't talk this morning. They get contaminants on the gloves, and then they grab the splice body and go to sliding it on, and before you know it, we've got contaminants on the cable itself. So I always had my guys clean their hands and use bare hands when putting the splice together or sliding a terminator elbow or a terminator onto the cable. So, to each his own, whatever company chooses to do. Crimping the connector, I kind of mentioned this earlier, but you want to make sure that you're using the correct dies to start with, and then maybe rotate so that you don't actually put a little twist onto the conductor itself when crimping. Having the splice body on, you can see the boot, the pull boot that's on the right hand side. They put it underneath. But what I wanted to mention here, he's actually got his glove over the top of it, but it's always a good idea. We call this a bleed wire. Some companies have called it a ground wire. So it goes into the eye of the splice body, and it's a bleed wire. Why is it a bleed wire? Well, I mentioned the cable and the stresses and creepage distances. So first off, our splice body is keeping all of the stress that's coming through that insulation outwardly and evenly. But like I mentioned earlier, you also have that little bit of amperage loss, that creepage distance that's going through the insulation, and it needs to have that semiconductor shield on top. Now, that splice body could actually carry some amperage. And, carrying a little bit of amperage is no big deal unless we get some voltage. So what I'm going to talk about at the end here is those concentric wires. And they're connected. So until they're bonded together here in the middle, they create a different hazard that I'll cover in about 10 minutes. All right, so the completed product, this company uses a cold shrink to prevent any moisture from entering the cable jacket. And the 3 splices that we talked about earlier are identified. We have them all taped and identified. Anybody coming along will know what phase goes to what. This is the 3 phases in one cable. So it's actually 3 different conductors all in one. You see a lot of this in the islands, and that's actually where these pictures were taken from. Some of the Caribbean islands use these. And it's a total overall jacket. They have some different types of concentrics that's on here. So it's actually a concentric tape that's bonded together on this cable. Back in the day, before we had splice kits, we had tape splices. I have put together, back in the late 70s, many of these tape splices, and basically it's just layer after layer after layer, but it's all got the same concept. You have the insulation, you put some insulation layer on there, you put some semiconductors so that those stress lines go out evenly, and then you put some tape over the top and then some more tape over the top and bind the concentrics together. There's also the heat shrink tubes. You can see the 3 different tubes. There's the one insulation, or the one conductor tube, which provides a an even roundness onto the conductor. The second one is your insulation layer. So it actually use it. It actually works exactly like the insulation that's on the cable itself. And then the outer is a semiconductor, and then you would have some other kind of sealant or something that's on top of that one. These are all heat shrink tubes, and you should always use the proper heat to shrink them, and make sure that you use it properly, know how to use that kind of thing. All right, high voltage terminations. This is what we call a pothead. And the reason it's called a pothead is back in the late 70s, 60s, and 70s, when these terminators were put together, it was actually a large porcelain pot. So you would make up the cable, stick it into the pot, pour some resin in there to evenly allow the stress around it. Okay. So that's why you got the term pothead, and it just stuck. So some things I want to show on this pothead is right here you see the concentric wire coming down, and actually it connects to the bottom of this lightning arrestor and then to the system neutral. Here the arrestor comes and actually makes a tap onto the conductor coming up from the pothead into the bottom of the cutout. So this company puts an arrestor next to their underground system, and this is the pothead, although it's a lot smaller than the splice body or an elbow. It actually just does the same thing. The skirts allow for moisture and environmental conditions to go around and actually give more of a surface for that current leakage. All right, talk a little bit about insulation and a typical K factor of insulation. I mentioned early on we have paper insulated lead sheath cables. So solid paper gives a 3.7 K factor, which is just a type of measurement for measuring your insulation on your cables. There's an oil filled, and most of your solid paper is an oil filled type paper, 3.5. There's a gas filled. Very expensive cables. I don't know of any that are left in use today. Most of them, it was so expensive to splice, most of them just got replaced. Varnished cambric, I have no idea what that is. I have never heard of varnished cambric. And then the rubber, so your cross-linked polyethylene is right in there with the rubber at 6.0, and then a capacitive material. So the semiconductor material that we're talking about. Here's sliding on that terminator onto the cable, and just making sure that we're using all the right tools and not damaging the potheads. When I come on site, we do splices, potheads, and terminator elbows so that everyone knows how to read the instructions. Here, squeezing the concentric to the system neutral. It's always aluminum over copper, something that we always add in there. 3 different types of transformers. You got your dead front, top left, your live front, top right, and then load break elbows. If you notice these load break elbows, they all have a white stripe on them. So that indicates to us that they're a load break elbow. If they do not have a white stripe, it could be that they do not have the ablative tip. So on the right-hand side, you see the ablative arc extinguisher tip, and that's what makes it load break. So actually inside of, and thanks to Jerry for these 3D models, inside we have the transformer bushing, which comes all the way out to here, and it makes a little locking right here. There's actually some teeth that are on the metal probe contact. So when you pull the elbow out of the bushing, this ablative tip actually suppresses the arc. All right, we have the semiconductor. You notice that at the end of the semiconductor shield down here, it begins to expand. And again, that takes those stress lines and makes them go outward and evenly. Here at the end of the insulation, where the conductor connector is, then we have some airspace, very important in that airspace to allow all of the load, all of the current leakage to go out. And then down here is an eye. A lot of folks call this a grounding eye, and it is not a ground eye. It will not ground the elbow. It allows for bleed off from all of the current leakage coming through this elbow to try and create a safe atmosphere in case there's an inadvertent touch on that elbow from a worker. So you might have rubber gloves on. Some companies don't require rubber sleeves, so the gloves only come to the top of the elbow. If I'm working inside, my elbow may touch this elbow inadvertently while I'm working on the secondary side, and that should be bleeding off some of that wire. So that's all part of the inspections. I won't have time to get into the inspections. Here are bolted on elbows. These are 800 amp elbows bolted onto a switch gear. You actually have a cap that's behind them. That cap can be pulled off, and we can actually make it like add a bushing on there and add another 200 amp elbow onto this phase if we needed a tap or things like that. So very, very versatile. These are relays. This is actually a switch gear that has relays in an automatic switching scheme. Again, I wanted to get a close-up of this crimping tool, squeezing the ferrule. Always rotate the press, and it depends on the type of dies. There are some dies out there that you do need to crimp it straight. So know what kind of dies you're using. This is the chamfer tool that I mentioned earlier. What it does is when you're putting on an elbow or some splices, always follow the instructions. It requires that you make a chamfer on the end of the cable. So you've just made up the cable. It's got a sharp edge on it. Sliding the elbow on or the splice body on could actually damage some of the inside of the elbow and leave a scarring mark that would leave a track for later on when we bind it up. So the chamfer tool actually smooths that off, so when you're sliding the elbow on, it makes a smoother process. There's the drain wire that I mentioned. It gets wrapped around to actually bleed off any leakage current that may be coming through. There's the transformer bushing that the elbow would go on to. Here is a three-phase pad mounted transformer, and I wanted to bring this out because some of your older transformers, this one has switches, which makes everything very safe. We can actually open and close, so you can see that these switches are open. So these, all three of these transformer bushings, all three of these transformer bushings are actually turned off. If you have a transformer that does not have a switch, so if this is plugged in and all of these are energized, we have an energized bushing in the transformer right here. And like I mentioned, the teeth that are right close to the end, and depending on the voltage, if we're putting on an elbow and we twist it and we have this grounded concentric wire that is right over the top, it can arc out and cause a fault. So this should have actually had a bushing cover on it for doing this. They opened the switches and did that, but the company that did this did not actually do this wrong. I had them twisted so that we could get a picture and show what some companies may, in a sense, do wrong. All right. Here's a terminator going into a switch gear. Cold shrink termination, a little bit better look. Basically, it just does the same thing. It makes the stress go out evenly, and it bolts up to the switch gear. Here's this company. They require gloves, sleeves, hard hat, safety glasses, and a face shield for doing live line switching. So they're actually energizing the cables in a switch gear here. Switches to open and close the transformer bushings. I mentioned that already. Here's why we do a good inspection on a transformer. This was actually in a switch gear, and that switch gear that I showed you earlier, this was the ground rod that was down in there. I got a good close-up picture of it. We actually had a ground rod on the other side of this piece of equipment that gave us a good grounded bond, so I wasn't that worried about it, and they were all tied together. We actually opened up this part of the switch gear. I saw this and I asked the question. We had 15 people on site. I asked the question, okay, have we inspected this transformer, this switch gear? And all 15 said, oh, yes, we've been in here. As a matter of fact, we were in here just last week. 7 guys were in here just last week. And I said, well, this corrosion did not happen within the last week. So if you've been inspecting your ground rods, you have not been doing a very good job of it. And never touch a cabinet until the inspection is complete, and never let anybody hang on the doors. This is one of my big pet peeves. Do not allow employees to hang on to doors when doing any switching or doing anything. Keep them off of there. All right. And the system neutral concentric, I'll end with this. What about the concentric? We cut it in half to make a splice. Is there any current flow? All right. On our overhead system, 3-phase overhead system, what does the system neutral do? And because I'm not getting any of your questions or answers or anything, I'm going to answer it for you. It is a return current back to the source. So if we have 3 phases, whatever the difference in amperage on those 3 phases is, and I don't know any 3-phase system anywhere that is totally balanced in amperage. So there's going to be some difference. So whatever that difference is, that amperage or return current is going back to the source on the system neutral. And then a single phase system neutral is just returning the current back to the source. So our system neutrals are always containing current. That's why we ground them at every pole, or every so often on every pole, every piece of equipment or whatever. But that's why we ground. And then on the overhead system, if you remember several years ago, the ground wire that came down the pole actually had a little U-shaped cover, whether it be wood or plastic, on top of it. What do you think that was for? That was to protect the public from coming in contact with that ground wire, which is connected to the system neutral, which is carrying current. So we've determined over time that the current level is so small, so slight, that it's not really a hazard to the public any longer. However, if we have a car hit the pole and one of the conductors comes down and energizes that neutral, it also energizes that ground wire. So that's where the hazard is. And, do cars always hit poles? Well, in our line of business, it does happen more frequently than you suspect. Does trucks grab guy wires and get conductors together? They still do. We had one that was reported about 2 weeks ago, I believe. And the conductors got together, burned down, actually contacted the neutral, and energized the neutral with the current carrying conductor. Okay, so in our underground systems, is the concentric neutral a neutral current carrying conductor? The answer is yes, it is. So when we're in a transformer and we're making up an elbow, or we're replacing an elbow, and that concentric is still connected all the way through the system. And for instance, and I think I have a picture of this. Let me go on through to the picture and talk about the concentrics a little bit. We actually plump transformers when we cook them. Bayonet fuses shall only be operated after pad mount transformers have been properly vented. This was actually a ferrule resonance type of burnout. The cable feeding this transformer was over 1,500 feet of URD cable. We lost one phase had faulted, and the load was removed. And when the load was removed, we had enough current buildup in the other two uh, transformer windings that actually made it about 3 times higher the voltage, and we wasn't insulated enough for that. So they plump when you cook them. All right, so I'm looking and I don't have my diagram for that concentric neutral, but in any case, we have a concentric neutral that's connected on both sides. We've switched out the primary cable to replace elbows or whatever, but that concentric neutral is still connected. It is a current carrying conductor, so if we ever get any voltage potential difference in there, will it shock us? And the answer is yes, it might. Okay, so it's not a real big hazard, but it is a hazard that I like to bring up in all of my training. If we're making a splice, what we should do on each end of that cable is just get a bond, any kind of bond that would bond those two together, so that when we go to grab them and put them back together, we're not getting in between that current carrying conductor. Would you ever cut an overhead neutral and get between it? And the answer for every line worker in the industry is no, it will kill you. But yet we do this on underground cables all the time. I've done it for 20 years and never really thought of anything about it until, well, I've done it for about 10 years, because after that, it became a hazard. We actually had to make a splice in a rear lot. We dug a hole, we found the fault, we cut out about 2 feet of cable, and so we were putting two splices back together. The thing was, the way that the system was put together, the cable on the left-hand side came out of one substation, and the cable on the right came out of another substation. They phased together, but out of two different substations, we had two different amounts of load. So I got down in, we had the splices all together. I got down in and squeezed one concentric neutral and went to squeeze the other. When I grabbed the two, I got a shock. And, it wasn't bad. It was enough to make me let go of it. So from then on, concentric neutrals became hazards. I went back and started asking engineer questions as to, okay, what happened? And they explained to me what happened, and explained to me also what the hazard was. So basically, we have a lot of underground hazards out there. You can see on this transformer, the bushing actually blew out of this transformer. So I don't know what it was that caused the fault on here, but in any rate, if this cable is actually being fed from another direction, then it could still be energized. So when I come and I want to know why this transformer is not energized, I would unlock the lock, unbolt the bolt down here, grab this lid and open it up, and possibly this elbow would fall out and make contact, if it's still energized, with this part of the transformer cabinet. I have seen that before. I've also seen where transformers like this, all the secondaries are coming up and going in front of the primary conductors. And I've seen guys working on this part and actually make the elbow back off of the bushing. So just some things that we need to watch out for. Here's that vent. You would never pull this bayonet fuse out unless you vent it, because if you do, all that oil that's going to come in there comes shooting out. So that's the quick down and dirty. We have about 3 more hours of training that we actually spend on this when we're on site. And then we actually go out and inspect transformers and make up terminators, make up splices, talk and show more of how the stress works on real cables out in the field, and cover the different types of tools, the different kinds of tools. And again, we don't promote any one type or brand of tool at this company. We just use whatever the company actually happens to have. and we welcome any donations. If your company has some tools that you would like us to get pictures of for the next presentation, we would be much more happy to be able to do that. That just about covers my hour of time. So if we don't have any comments or questions, uh, thank you for all of you who were on. At the beginning of this presentation, I had my name and number up there. I can go back to it one more time, I believe. And that way y'all have my contact information. I think I can do it. So this is so much better when folks have comments and questions. The ISPC, just go to Institute for Safety and Powerline Construction, get on the website. Our phone numbers are there, Mac Turner, Jim Vaughn, and myself. So thank you for everyone who's endured my stumbling through this presentation today. It's just so much harder to talk to a laptop than it is to talk to people. So invite us now that states are starting to open up. Now that Texas and Mississippi is open, we're getting more and more on-site recommendations and requests. I'll get it out here in a minute. So thank you so much for being on. Ryan, do you want to wrap up anything in here?
Yeah, no, we appreciate your support. And again, we do have a donation button there in the chat for you to donate, even if it is a dollar. We appreciate anything that you can give. And thank you all for attending today.
Thank you. Tony out.
All right. Thank you all. Appreciate it.